Hello everyone. In today's lecture, we will study how calculus connects one-dimensional change, two-dimensional area, and three-dimensional space. The main title of this lecture is From Dimensions of Change to the Geometry of Space. The subtitle is An Architectural Blueprint of Advanced Calculus. This means that we will not study calculus as separate formulas only. Instead, we will understand calculus as a system. We will see how a simple line segment becomes a circle and how a circle becomes a sphere. In other words, we will move from one dimension to two dimensions and then to three dimensions. On the slide, we can see three important ideas. First, in one dimension, we have a line segment. The length of a small line segment can be described as a small change in x. We can say this verbally as length equals change in x. Second, in two dimensions, we have a circle. The area of a circle is described by the formula area equals pi times radius squared. Third, in three dimensions, we have a sphere. The volume of a sphere is described by the formula. Volume equals 4 over 3 times pi times radius cubed. This slide gives us the big picture of the whole lecture. Calculus helps us measure change, area, and volume. It helps us move from a simple line to a plane shape and then to a physical solid. So, the main question of this lecture is how does calculus transform algebraic functions into geometric meaning? This slide introduces the complete journey of the lecture. We begin with one-dimensional rates of change. This is the world of derivatives. In one dimension, we ask questions such as how fast is something changing, how steep is the curve, how does one quantity respond when another quantity changes. In this part, the mathematics includes higher order derivatives and the Leibniz rule. Higher order derivatives mean that we take the derivative again and again. The first derivative gives us the rate of change. The second derivative gives us the rate of change of the rate of change. In geometry, this often tells us about concavity. In physical systems, it can describe acceleration or structural stress. The second part is two-dimensional structural analysis and accumulation. Here, we study optimization tests and definite integrals. Optimization means finding maximum or minimum values. Definite integrals help us calculate exact area under curves or between boundaries. In simple words, two-dimensional calculus helps us answer questions such as where is the best point, where is the largest area, where is the smallest distance, how much area is enclosed by a curve. The third part is three-dimensional physical construction. Here, we use volumes of revolution, especially the disk method. This means we rotate a two-dimensional curve around an axis and create a three-dimensional object. For example, if we rotate a semicircle, we can create a sphere. If we rotate a line segment or a curve, we may create a cone, a truncated cone, or another solid. So this slide shows that calculus is a journey. It starts with change, continues with area, and finally reaches volume. This slide explains the idea of successive differentiation. The base function shown on the slide is a power type function. It can be read verbally as E equals open parenthesis a minus b x close parenthesis raised to the power m. This function has an inner expression which is a minus bx and an outer power which is m. When we differentiate this function once, we apply the chain rule. The power m comes down in front, the power decreases by 1. Then we multiply by the derivative of the inside expression. Since the derivative of a minus bx is negative b, we multiply by negative b. So the first derivative can be explained as the first derivative equals m times open parenthesis a minus bx close parenthesis raised to the power m minus 1 multiplied by negative b. Now, when we differentiate again, the same pattern continues. The power becomes m minus 1. This power comes down, the exponent decreases again, and again we multiply by negative b. So the second derivative becomes mim times m minus 1 times open parenthesis a minus bx close parenthesis raised to the power m minus 2 multiplied by negative b squared. For the third derivative, the same structure continues. M times m minus 1 times m minus 2 multiplied by open parenthesis a minus bx close parenthesis raised to the power m minus 3 multiplied by negative b cubed. The important point here is not only the formula, the important point is the pattern. Each time we differentiate, three things happen. First, the current power comes down. Second, the exponent decreases by 1. Third, another factor of negative b appears because of the chain rule. At the bottom of the slide, the general formula is presented. We can explain it verbally like this. The nth derivative equals made factorial divided by m minus n factorial multiplied by negative 1 raised to the power n multiplied by b raised to the power n. multiplied by open parentheses a minus bx close parentheses raised to the power m minus n. This general formula is useful when we need the derivative many times. Instead of differentiating step by step repeatedly, we can use the pattern directly. The key idea is this: successive differentiation is not random, it has an architecture. The power decreases in a predictable way, and the chain rule contributes the repeated factor from the inside function. This slide introduces the Leibniz rule, which is used to find higher order derivatives of products. The function on the slide is y equals e raised to the power x times x raised to the power n. This function is a product of two parts. The first part is e raised to the power x. The second part is x raised to the power n. The special thing about e raised to the power x is that its derivative is always itself. If we differentiate it once, twice, or many times, it remains e raised to the power x. The second part, x raised to the power n, changes when we differentiate it. Its power decreases step by step. The code Leibniz rule can be explained verbally as follows: the nth derivative of a product equals the sum from k equals 0 to n of n choose k multiplied by the n minus k derivative of the first function multiplied by the kth derivative of the second function. This may sound complicated, but the idea is simple. When we differentiate a product many times, the derivatives can be distributed between the two functions in different combinations. The binomial coefficient tells us how many ways those combinations occur. In this slide, we choose u equals e raised to the power x and v equals x raised to the power n. The derivatives of u remain the same. The derivatives of v follow polynomial decay. For example, x to the power n becomes n times x to the power n minus 1. Then it becomes n times n minus 1 times x to the power n minus 2, and so on. The final output on the slide shows that the nth derivative can be written as e raised to the power x multiplied by the sum from k equals 0 to n of n choose k multiplied by k factorial multiplied by x raised to the power n minus k. In simple words, the exponential part stays stable, while the polynomial part gradually loses its power. The Leibniz rule organizes all the possible derivative combinations. This is why the slide calls it a machine. It takes a product as input, applies a systematic differentiation rule, and produces a structure output. This slide studies the function f of x equals x plus 1 divided by x. We are interested in finding local maximum and local minimum values. To do that, we first use the first derivative. The first derivative is f prime of x equals 1 minus 1 divided by x squared. To find critical values, we set the first derivative equal to 0. So we say 1 minus 1 divided by x squared equals 0. This leads to x squared equals 1. Therefore, the critical values are x equals positive 1 and x equals negative 1. Now we analyze what happens near these points. Near x equals negative 1, the first derivative changes from positive to negative. When the first derivative changes from positive to negative, the graph goes upward first and then downward. This means we have a local maximum. So at x equals negative 1, the function has a local maximum. When we substitute negative 1 into the function, we get negative 1 plus negative 1, which equals negative 2. Therefore, the local maximum value is negative 2. Near x equals positive 1, the first derivative changes from negative to positive. When the first derivative changes from negative to positive, the graph goes downward first and then upward. This means we have a local minimum. So at x equals positive 1, the function has a local minimum. When we substitute positive 1 into the function, we get 1 plus 1, which equals 2. Therefore, the local minimum value is 2. Now we also check the second derivative. The second derivative is f double prime of x equals 2 divided by x cubed. At x equals negative 1, the second derivative becomes negative 2. Since this is less than 0, the curve is concave down. This confirms a local maximum. At x equals positive 1, the second derivative becomes positive 2. Since this is greater than 0, the curve is concave up. This confirms a local minimum. There is an important warning on this slide. The local maximum value, negative 2, is numerically smaller than the local minimum value, positive 2. This may seem strange, but it happens because the function is not continuous at x equals 0. So we must remember, local maximum and local minimum are not always about the largest and smallest values in the usual global sense. They describe behavior near a point. This slide studies the function f of x equals absolute value of cosine x. Instead of only using derivatives, this slide emphasizes geometric understanding. Cosine x is related to the horizontal coordinate of a point moving on the unit circle. The value of cosine x always stays between -1 and +1. But here we are using the absolute value of cosine x. Absolute value means all negative values become positive. Therefore, the absolute value of cosine x always stays between 0 and 1. The maximum value is 1. This happens when cosine x is either +1 or -1. After taking absolute value, both become 1. The slide states that the absolute maximum value is 1. It occurs at x equals 2k pi, where k is any integer, and also at odd multiples of pi because cosine becomes -1 there and absolute value turns it into +1. The minimum value is 0. This happens when cosine x equals 0. Cosine x is 0 at odd multiples of pi over 2. So we can say verbally the absolute minimum value is 0 and it occurs when x equals open parenthesis 2k plus 1 close parenthesis times pi over 2 where k is an integer. The key insight is that trigonometric optimization can often be solved using geometry. We do not always need complicated derivative equations. If we understand the unit circle, we can identify maximum and minimum values directly. This is important because calculus is not only symbolic manipulation, it is also geometric reasoning. This slide shows optimization under a constraint. The given boundary is x divided by 2 plus y divided by 3 equals 1. We can solve this for y. Multiplying and rearranging gives y equals 3 minus 3x over 2. This line becomes the boundary for two optimization missions. The first mission is to maximize area. The area is represented by p equals x times y. Since y equals 3 minus 3x over 2, we substitute this into p. So p of x becomes x times open parenthesis 3 minus 3x over 2 close parenthesis. That simplifies to p of x equals 3x minus 3x squared over 2. Now we differentiate p. The derivative is p prime of x equals 3 minus 3x. To find the maximum, we set this derivative equal to 0. So 3 minus 3x equals 0. This gives x equals 1. Now substitute x equals 1 into the boundary equation. Then y equals 3 minus 3 over 2. So y equals 3 over 2. Therefore, the maximum area x times y equals 1 times 3 over 2, which equals 3 over 2. The second mission is to minimize distance. The squared distance from the origin is usually written as s equals x squared plus y squared. After substituting the boundary equation into this distance function, the slide gives s of x equals 13x squared over 4 minus 9x plus 9. Now we differentiate. The derivative is s prime of x equals 13x over 2 minus 9. Set it equal to 0. 13x over 2 minus 9 equals 0. Then x equals 18 over 13. Now we substitute x into the boundary equation. The corresponding y value is y equals 12 over 13. The minimum distance squared becomes 36 over 13. This slide is very important because it shows how a two variable problem can become a one variable problem. The constraint allows us to replace y with an expression in x. After that, we can use ordinary derivative methods. The general strategy is first write the constraint, second solve the constraint for one variable, third substitute into the target function, fourth differentiate, fifth set the derivative equal to 0, sixth interpret the result. This slide gives two major integration strategies. The first strategy is integration by parts. Integration by parts is useful when the integrand is a product of two different types of functions. For example, an algebraic function multiplied by a trigonometric function or an algebraic function multiplied by an exponential function. The formula can be read verbally as the integral of u dv equals uv minus the integral of v du. Here u is the part we choose to differentiate, dv is the part we choose to integrate. The practical tip is choose u as the part that becomes simpler when differentiated. Choose dv as the part that can be easily integrated. For example, if we have x times sine x, we usually choose x as u because the derivative of x is 1, it becomes simpler. We choose sine x dx as dv because sine x can be integrated easily. The second strategy is algebraic substitution, also called u substitution. This is useful when we see an inner function and also see a multiple of its derivative in the integrand. The verbal formula is the integral of f of g of x times g prime of x dx becomes the integral of f of u du. This means that we replace the complicated inner expression with u. then its derivative becomes du. This transforms the integral into a simpler form. The slide also gives an important tip for definite integrals. When we use substitution in definite integrals, we should change the boundaries immediately. The original boundaries are in x space. After substitution, the new boundaries must be in u space. This prevents confusion and makes the calculation cleaner. This slide applies integration by parts to the target integral, the integral of x times sine x dx. We choose u equals x, then du equals dx. This is good because x becomes simpler when differentiated. Next, we choose dv equals sine x dx, then v equals negative cosine x. Now we use the integration by parts formula. The integral of u dv equals uv minus the integral of v du. Substituting the parts gives the integral of x times sine x dx equals x times negative cosine x minus the integral of negative cosine x dx. This becomes negative x cosine x plus the integral of cosine x dx. The integral of cosine x is sine x. Therefore, the final answer is negative x cosine x plus sine x plus c. Here, c is the constant of integration. The important lesson is that integration by parts is like disassembling a product. We separate the product into one part to differentiate and one part to integrate. Then we reassemble the result using the formula. For H in pronunciation, this result can be spoken as the final answer is negative x cosine x plus sine x plus the constant c. This slide explains substitution using a definite integral. The integral shown is from x equals 1 to x equals 3 of x plus 2 divided by x squared plus 4x plus 5 dx. The key observation is the relationship between the numerator and the denominator. The denominator is x squared plus 4x plus 5. Its derivative is 2x plus 4, that is equal to 2 times open parenthesis x plus 2 close parenthesis. The numerator is x plus 2, so the derivative of the denominator is exactly twice the numerator. This is a perfect case for substitution. We define u equals x squared plus 4x plus 5, then du equals 2 times open parenthesis x plus 2 close parenthesis dx. So 1 half du equals open parenthesis x plus 2 close parenthesis dx. Now we change the boundaries. When x equals 1, u equals 1 squared plus 4 times 1 plus 5. That gives 1 plus 4 plus 5, which equals 10. So the lower boundary becomes u equals 10. When x equals 3, u equals 3 squared plus 4 times 3 plus 5. That gives 9 plus 12 plus 5, which equals 26. So the upper boundary becomes u equals 26. Now the original integral becomes 1 half times the integral from 10 to 26 of 1 over u du. The integral of 1 over u is natural log of u. So we get 1 half times natural log of u evaluated from 10 to 26. Now substitute the boundaries. 1 half times open bracket natural log of 26 minus natural log of 10 close bracket. Using the logarithm rule, this becomes 1 half times natural log of 26 divided by 10. 26 divided by 10 simplifies to 13 divided by 5. Therefore, the final answer is 1 half times natural log of 13 over 5. The main concept is that substitution transforms a complicated x space problem into a simpler u space problem. This slide explains how to calculate a bounded two-dimensional area. The region is bounded by the curve y squared equals 4x. We isolate the positive branch. Taking the square root gives y equals 2 times square root of x. The region is bounded by the x-axis and the vertical lines x equals 4 and x equals 9. So the area is calculated using a definite integral from 4 to 9. Area equals the integral from 4 to 9 of 2 times x raised to the power 1 half dx. Now we integrate. The integral of x raised to the power 1 half is x raised to the power 3 over 2 divided by 3 over 2. Dividing by 3 over 2 is the same as multiplying by 2 over 3. Since there is already a coefficient 2 outside, the result becomes 2 times 2 over 3 times x raised to the power 3 over 2. That simplifies to 4 over 3 times x raised to the power 3 over 2. Now evaluate from 4 to 9. At x equals 9, 9 raised to the power 3 over 2 means square root of 9 cubed or 3 cubed. That equals 27. At x equals 4, 4 raised to the power 3 over 2 means square root of 4 cubed or 2 cubed. That equals 8. So the area becomes 4 over 3 times open parenthesis 27 minus 8 close parenthesis. 27 minus 8 equals 19. Therefore, area equals 4 over 3 times 19. which equals 76 over 3. So the total bounded area is 76 over 3 square units. This slide shows how integration accumulate infinitely thin vertical slices to calculate a complete two-dimensional area. This slide moves from two-dimensional area into three-dimensional volume. The method used here is the disk method. The logic is when a curve is rotated around an axis, it creates a three-dimensional solid. This solid can be divided into infinitely thin circular disks. Each disk has a radius and a small thickness. The volume of each small disk is approximately pi times radius squared times thickness. In calculus notation, the full volume is the integral of these disk volumes. Verbally, the formula is volume equals pi times the integral from a to b of f of x squared dx. Here, f of x gives the radius of each disk. The small thickness is dx. The example on the slide uses y equals x squared from x equals 0 to x equals 2, so the radius is x squared. The volume becomes pi times the integral from 0 to 2 of open parenthesis x squared close parenthesis squared dx. Open parenthesis x squared close parenthesis squared becomes x raised to the fourth power. So volume equals pi times the integral from 0 to 2 of x raised to the fourth power dx. Now integrate x to the fourth power. The integral is x raised to the fifth power divided by 5. So the volume is pi times x raised to the fifth power divided by 5. Evaluated from 0 to 2. At x equals 2, 2 raised to the fifth power is 32. At x equals 0, 0 raised to the fifth power is 0. Therefore, the volume is pi times 32 over 5. So the total volume is 32 pi over 5 cubic units. The key idea is that the disk method changes an area idea into a volume idea. We are no longer only measuring under a curve. We are rotating the curve to build a solid. This slide gives two examples of solids created by rotation. The first example is a sphere. The curve is y equals square root of 9 minus x squared. This is the upper half of a circle with radius 3. If we rotate this upper semicircle around the x-axis, we create a sphere. The volume is calculated by the disk method. Volume equals pi times the integral from negative 3 to positive 3 of 9 minus x squared dx. Because the function is symmetric, we can double the integral from 0 to 3. So we say volume equals 2 pi times the integral from 0 to 3 of 9 minus x squared dx. Now integrate. The integral of 9 is 9x. The integral of x squared is x cubed over 3. So the expression becomes 2 pi times open bracket 9x minus x cubed over 3 close bracket evaluated from 0 to 3. At x equals 3, 9 times 3 is 27. 3 cubed is 27 and 27 divided by 3 is 9. So 27 minus 9 equals 18. At x equals 0, the value is 0. Therefore, the volume is 2 pi times 18, which equals 36 pi. So the sphere has volume 36 pi cubic units. The second example is a truncated cone. The curve is y equals x plus 1 from x equals 0 to x equals 2. When this line rotates around the x-axis, it creates a solid similar to a truncated cone. Using the disk method, volume equals pi times the integral from 0 to 2 of open parenthesis x plus 1 close parenthesis square dx. Now expand the square. X plus 1 square equals x squared plus 2x plus 1. So we integrate x squared plus 2x plus 1. The integral becomes x cubed over 3 plus x squared plus x. Evaluate from 0 to 2. At x equals 2, x cubed over 3 becomes 8 over 3. X squared becomes 4. X becomes 2. So the total is 8 over 3 plus 4 plus 2. 4 plus 2 equals 6. 6 equals 18 over 3. 8 over 3 plus 18 over 3 equals 26 over 3. Multiplying by pi gives 26 pi over 3 cubic units. So the volume of the truncated cone is 26 pi over 3 cubic units. This slide shows that many familiar geometric objects can be constructed by rotating simple curves. This final slide summarizes the entire lecture. Calculus is not just a list of rules, it is a connected system. In Module 1, derivatives answer the question, how steep is this edge? This means derivatives help us measure slope and rate of change. In Module 2, optimization answers the question, where is the structure widest? This means calculus help us find maximum and minimum values. In Module 5, area and integrals answer the question, what is the exact area of this cross-sectional face? This means integration helps us accumulate many small slices to calculate a complete area. In Module 6, volumes answer the question, how much total physical space does this command? This means integration can also construct and measure three-dimensional objects. The figure in the middle of the slide represents a solid shape. Around this shape, all calculus ideas come together. Derivatives describe how the shape changes. Optimization finds important points. Integrals calculate area. Volume methods calculate three-dimensional space. The synthesis takeaway is very important. Calculus is not a list of separate rules. It is a continuous translation engine connecting algebraic forces to geometric realities. In simpler words, calculus converts equations into shapes, change into structure, and formulas into physical meaning.